Okay, now students, there is a difference between previous problems of time division multiplexing and now the problems what we are solving. What the difference is, now if you observed or not, all the previous problems, each signal band limited to 5 signals, band limited to 5 signals, each band limited to 10 kHz. Means all 5 signals are band limited to 30 kHz. All 10 signals are band limited to 5 kHz. All 20 signals are band limited to some 10 kHz, something else. But now in the question, a signal's frequencies are different. Means first signal at one frequency, second signal at some other frequency, third signal at some other frequency. So in such a situation, then how we are solving the problems? Means now signals are having different frequencies. If the signals are having different frequencies, how to fix speed of commutator? But previously there is no issue because all signals are having same frequency. Therefore, we can easily find the sampling rate, that itself will be the speed of the commutator. But now first signal is at some other frequency, second signal is at some other frequency. Then how to fix the speed of the commutator? There are two methods to fix the speed of the commutator. One is based on highest frequency, and the second one is based on lowest frequency. So when we choose the highest frequency method or when we choose the lowest frequency method, we will see. Okay, now we'll solve the problems wise, you can easily understand. Okay, now we'll solve question number 14. This one is question number 14. Then this is a commutator. Now this is the first message signal, M1 is at 1 kHz. Now this is the second message signal. Now this is at 2 kHz. Now this is quantization and encoder. Encoder is also given. I think this is a 10-bit A to D converter. 10-bit A to D converter. Now he is asking to find bit rate RP. What is the problem here? Now if you see, previously all signals are 2 kHz, all signals are 10 kHz, all signals are 5 kHz. But now first signal is at 1 kHz, second signal is at 2 kHz. Now signals are having different frequency, right? Now how to find that? So can I write like this? Now the sampling rate here, which is equal to, now here the sampling rate which is nothing but the Nyquist rate. Now what is the Nyquist rate here? 2 omega. 2 omega is 1, therefore 2 kilo samples per second. Now if the second signal is also sampled at 2 kilo samples per second, what happens? If the second signal is also sampled with 2 kilo samples per second, then what happens? Aliasing effect will occur. Aliasing effect, undersampling, because the minimum rate is 4 kilo, but you are done at a lesser than the Nyquist rate. The sampling rate is less than the Nyquist rate. The Nyquist rate is 4 kilo, but you do the signal sampling with less than the Nyquist rate. The sampling rate which is less than the Nyquist rate, aliasing effect, distortions will occur. Therefore, you should not do like this. So can I do like this? Now the second signal is sampled at minimum rate, which is nothing but 2 omega, 2 into 2, 4 kilo, which is equal to 4000 samples per second, then not a issue if the signal 1 is also sampled at, if the signal 1 is also sampled at 4 kilo, which is nothing but 4000 samples per second, because the minimum rate required is 2 kilo, but you do the signal sampling at 4 kilo, the sampling rate is greater than the Nyquist rate, oversampling, which is a good practical filtering is available here. Okay, so this is the advantage, right? Now this is the sampling rate, this is the sampling rate. Therefore, what is the speed of the commutator? Therefore, this is 1 by Ts, which is equal to 4000 samples per second. Therefore, Ts, which is equal to 1 by 4 kilo, which is equal to 0.25 millisecond. Okay. Now, this is Ts, which is equal to 0.25 milliseconds is the speed of the commutator. This is 0.25 milliseconds is the speed of the commutator. Now, this is quantization and encoding into 10 bits PCM system. Therefore, bitrate. What is the bitrate RB? Now, bitrate RB, which is equal to 1 by TB into M into N, because this is time division multiplexed signal. Okay. Now, M into N. Therefore, bitrate RB, which is equal to 1 by Ts into capital M into small n. Therefore, bitrate, which is equal to now 4 kilo into 2 into 10. Therefore, bitrate RB, which is equal to 4 into 2, 8 into 10, 80 kilo bits per second. Now, 80 kilo bits per second is a bitrate. Right. Now, this is the time division multiplex signal now with the different frequencies. But now here, what is the meaning of that? This is the speed of the commutator. You fix it based on highest frequency. Am I not? Now, this is omega 1. This is omega 2. This is the highest one. Now, you fix the speed of the commutator based on the highest frequency. Now, we'll see the same kind of problems. Now, see here. Now, the second problem is like this. Now, this is the commutator. Now, this is 1 kilohertz, same. Quantization, same problem. Encoding, now this is 10-bit A to D converter, and he is asking to find the bit rate. And if you want to find the bit rate, first we have to fix the speed of the commutator. Now here the number of bits are transmitted because the binary data. Okay. So now if you see here, now here this signal is sampled at Nyquist rate, which is nothing but 4000 samples per second. But the commutator switches at this particular position, then only the time taken to complete one revolution of the commutator. Am I not? Now at this T1 seconds, T2 seconds, T3 seconds, then Ts seconds time is completed. Therefore, now out of these 4000 samples per second, now what happened? Now definitely 2000 samples are collected here, and here there are 2000 samples. Am I not? Because actually here this is 4000. Now out of this 4000, now this is at this instant one sample, at this time interval one sample. Therefore 2000, and already this signal with a minimum rate of 2 kHz, which is nothing but 2000 samples per second. Now see, in this case, now the signal is sampled with 2 kilo samples per second, which is nothing but, now 1 kHz means Nyquist state is 2000, right? Now 2 kHz. Now in such a situation, now what is the speed of the commutator? Now 1 by Ts, which is equal to 2000 samples per second. Therefore, now the speed of the commutator Ts, which is equal to 1 by 2000, which is equal to 0.5 millisecond. Now this is the speed of the commutator. The speed of the commutator, now here this is 0.25 milliseconds. Now the speed of the commutator here, Ts, which is equal to 0.5 milliseconds. Now this is quantized and encoded. Okay. Now what is the bit rate now? Rb, which is equal to 1 by Ts into capital M into small n. Now Rb, which is equal to now 2 kilo, which is equal to, now what is M? Now this with respect to commutator, then it will be treated as three signals into, now number of bits is 10. Now therefore bit rate, which is equal to 60 kilo bits per second. Now this is the speed of the commutator. Now this is based on highest frequency, based on highest frequency of message signal, highest frequency of the signal. Now this is the speed of the commutator is based on, this is based on lowest frequency of the signal. This is the commutator which is fixed based on highest frequency of the signal, and this is the speed of the commutator is based on lowest frequency of the signal. Okay. Now this is the speed of the commutator is based on highest frequency and based on lowest frequency. So this is now which one is preferable? Now here a bit rate or a bandwidth of 60 kilo bits per second or 60 kilohertz. Now here a bit rate and bandwidth of 80 kilohertz. Now obviously we will prefer this one. Practically we are preferring to fix the speed of the commutator is based on lowest frequency, because it will occupy a bit rate and bandwidth is less. But if you take fixing the speed of the commutator is based on highest frequency, it will occupy more bandwidth and more bit rate, which is equal to 80 kilobits per second or 80 kilohertz. Now this is 60 kilobits per second or 60 kilohertz. Okay. Now this is the bit rate and bandwidth. Now you see here, this second method is preferable, but this method is valid with one condition. What is the condition? The condition is all the frequencies of the signal should be an integer multiples of a lowest frequency. Integer multiples of lowest frequency. N is an integer. All the frequencies of the given signal should be an integer multiples of the lowest frequency, then this method is valid. Yes. What is the first frequency? 1 kilohertz. 1 kilohertz, which is equal to integer multiples of lowest frequency is how much? 1 kilohertz. What is the second frequency? 2 kilohertz. Now, which is the integer multiples of the lowest frequency? What is integer multiples? Now, the integer multiples of integer multiple is 2 of lowest frequency is 1 kilohertz. Okay. Now therefore this method is valid if this condition is not satisfied. If all the frequencies are not the integer multiples of the lowest frequencies, you cannot use the fixing the speed of the commutator based on lowest frequency. You forcefully go for the fixing the speed of the commutator based on highest frequency. Even bitrate and bandwidth is increases. Okay. No. So here 2 signals but 3 samples to the commutator. So second signal is sampled twice. So in the examination he is not giving the diagrams like this. Okay. Now he is giving a theory questions, but for better understanding I am giving the sampling, quantization and encoding method. Okay. Now this is a quantized samples is encoded in terms bits. Now what is 3 signals? Now 3 signals having, this is actually question number 14. Now 3 signals having a bandwidth of 600 hertz, 1200 hertz, or sample at their respective Nyquist rate, quantized and encoded into 12 bits. Determine the bit rate. Okay, you do this problem. Now see here. Now we can fix the speed of the commutator is based on lowest frequency method or not. First you can check. Now what is the condition? The condition is nothing but all frequencies, or what is the lowest frequencies? 600 hertz. Then all the frequencies are integer multiples of the lowest frequency. All the frequencies are integer multiples of the lowest frequency. Therefore, first signal frequency is integer multiples of lowest frequency. Now second signal is, what is the second signal? Is also the integer multiples of the lowest frequency. What is the third signal? The third signal is also integer multiples of the lowest frequency. 1 into 600 edges, 2 into 600 edges is nothing but the 1200 edges. Therefore, all the frequencies are integer multiples of the lowest frequency. We can fix the speed of the commutator is based on the lowest frequency. But first signal is sampled, right? Now this is 1200 samples per second. Now this is 1200 samples per second. Now this is 1200 hertz. Now which is nothing but, now this is 2400. But now this signal is sampled twice. Am I not? Now this is 2400, but the signal is fixed based on the lowest frequency. Therefore, now this is sampled twice. Now the third signal, first signal is sampled once, second signal is sampled once, but third signal is sampled twice. 3 signals, but input to the commutator is 4. 1, 2, 3, 4. So commutator will treat it as a 4 signals. Okay. Now therefore this is 1200 samples per second. Here is also 1200 samples per second. Now we can fix the speed of the commutator is based on lowest frequency. Therefore, what is the bit rate? Now bit rate RB, which is equal to 1 by Ts into capital M into small n. Now which is equal to 1200 samples per second. M is 4, N is 12, which is equal to 57,600. Therefore, which is equal to 57.6 kilo bits per second is a bit rate. Okay, note down. Okay, now this method is valid when sampling rate is all the signal frequencies are integer multiples of lowest frequency. Now in these problems, if you observe, binary data is transmitted because sampling, quantization, encoding. But in some practical applications, samples are transmitted directly. In some practical applications, samples are transmitted. So, how that? Now this is a low pass filter. Now directly the samples are transmitted through the channel. So let us see, for example, a signal band limited to 10 kilohertz. A signal band limited to 10 kilohertz and sampled at Nyquist rate. What is the meaning of that? And sampled at Nyquist rate, which is nothing but Nyquist rate is 2 omega. Therefore, which is equal to 2 into 10 kilo. Therefore, Nyquist rate, which is equal to 20 kilo samples per second. Now, 20,000. How many samples? 20,000 samples. 20,000 samples are transmitted per second. Now, over a duration of 1 second, how many samples? 20,000 samples are transmitted. Now you tell me, to transmit 20,000 samples over a duration of 1 second, then how much bandwidth is required? So, to transmit 20,000 samples over a duration of 1 second, the bandwidth required is basic signal bandwidth itself. The bandwidth required is 10 kilohertz. Now these are the samples are transmitted over a duration of 1 second with a requirement bandwidth of 10 kilohertz. Channel bandwidth. Okay, which bandwidth? To transmit 20,000 samples over a duration of 1 second, required channel bandwidth is 10 kilohertz, which is the bandwidth of the signal itself. Okay, clear or not? But sometimes the question is like this. Now a question is 3 signals. 2 kilohertz, 6 kilohertz, 10 kilohertz. 2 kilohertz, 6 kilohertz, 10 kilohertz. Now you tell me, how many samples are transmitted over a duration of 1 second and how much channel bandwidth is required? Same. Now the signals are sampled with Nyquist rate. Therefore, this is nothing but 4 kilo, now 12 kilo, now 20 kilo. Means over a duration of Ts seconds. What is the Ts seconds? Over a duration of Ts seconds. Ts seconds is nothing but, now over a duration of 1 second. Over a duration of 1 second. How many samples? Now here 4000 plus 12,000 plus 20,000. So total, now 4 plus 2, 16 plus 20, 56. Oh, sorry. 20 plus 16. Oh, sorry, 12 plus 4. 16 plus 20, 36,000 samples are transmitted per second. Yes, 36,000 samples are transmitted per second. Now, how much channel bandwidth required to transmit? The channel bandwidth required to transmit 36,000 samples per second is, what is the bandwidth? 4, 12, 20 plus 32 plus 4, 36 kHz. Clear or not?